First of all, I'd like to say good afternoon to everyone, and thank you so much for inviting me to speak today. There we go. So I understand that you have a really dynamic core facility and that you have a Zeta sizer nano there. So you might have some background in dynamic light scattering and Zeta potential. If you want to break in during the presentation or just type in the chat some questions, I'll be happy to answer them. This is a fairly, I did include a lot of slides, but I am happy to alter those slides and meet your needs. So please feel free to send in questions. And we'll try to get to them. Anyway, so I started off with a broad brushed approach for just the concept that there are really a lot of different applications for studying nanoparticles, nanomaterials. And the really hot application areas that we see, I mean, we sell light scattering instrumentation, some microscopy methods, and a variety of scientific instrumentation to characterize materials. But the hot applications we see in nanoparticle technology is really when it comes to energy storage, things like batteries, hydrogen storage. There's energy generation in fuel cells and solar cells. We have a lot of applications that are along the drug delivery lines, targeting, cancer treatment, exosomes, protein aggregation. The companies that made the COVID vaccines all have Zeta sizers. They characterize those vaccines, by dynamic light scattering. Of course, aggregates in a vaccine would not be good. So it's really critical to use dynamic light scattering when you develop vaccines, as well as Zeta potential for improving the stability, as well as the pain threshold during the injection. So it's amazing how many different application areas. There's also a really growing application area in environmental applications, groundwater, water disinfection, bactericides, but you'll also see one of my final examples is on drinking water. I've spent the last 20 years really doing a lot of work with the water industry. So I'll try to give you some background with those slides as well. So like I said, there's really a broad range of applications where people are very interested in characterizing nanoparticles. And it's really a broad range. So just to start off with, you have solar cells. There's really two types. There's solar cells that generate electricity. There's hydrogen production through direct water splitting, where the characterization of nanoparticles come in play are with surface coatings. Silver and gold plasmonic particles are used in surface coatings on those cells. That coating increases solar efficiency and hydrogen conversion efficiencies. It really talking about the direct coating of gold particles on the silicon cells, and they improve the efficiency of the cells. Silicon doesn't absorb light very well, so these nanoparticles increase the Raman scattering to enhance the plasmon effect, which excites electrons and creates a current. So that's really where particle sizing becomes important. It's not just silver and gold, it's copper, indium, gallium, phosphorus, zinc, and alumina that are used in these coatings. So Like I said, solar cells are a big area. Fuel cells contain membranes that allow hydrogen ions to pass through the cell, but do not allow other atoms or ions such as oxygen to pass through. The top materials that we study for these fuel cells are solid oxides, gold nanoparticles, platinum particles. Platinum's very expensive. You have cobalt. There are platinum cobalt mixtures, and yttrium stabilized zirconium. But all of these materials really have to be characterized for particle size and size distribution in order to produce fuel cells. Paints and coatings are another big area. This is really an area that's gone through a dramatic transformation over the past 20 years. Paints had to move away from being organic based to, water dispersion based in order to improve, the ecological issues that were a problem for, volatile organic compounds. So many paints are now formulated in an aqueous base, and that requires more complex formulations. And that means that more characterization is needed. And that's really always true in these complex products. The fuel cells that I just showed on the last slide, the solar cells before that, the more complicated the product is, the more characterization you need in order to make sure that you obtain the properties, the final properties that you need for that product performance. So size and polydispersity, especially in paints, they really affect the appearance of that coating and the uniformity of that coating, how well that coating coats and covers a surface is all based on the size and the size polydispersity and the polydispersity of the size. Of course, the polydispersity can grow if the paint is not very stable. So a certain amount of stability also has to be built in, and that's why Zeta potential becomes very important when it comes to the paints and coatings applications. So you need to do the size measurement, Zeta potential, in order to determine the product stability, and understand the properties such as color and hiding power for these paints. Another big area is inks. New products are definitely on the horizon, which include printed electronics. There will be, in our near future, we'll see flexible displays. We'll see people painting their walls and just being able to light different areas of the wall based on how they paint it. Inkjet printed electronics will reduce production costs. It will simplify production of electronics. And so we need to be able to characterize inkjet inks. It's critical to the product performance. Again, it's the size that affects the color strength, the surface finish, the durability of that printed material. And of course, nozzle blocking is a big issue. So size plays a really big role in inks and inkjet printing. I know you have a Zetasizer, so you are definitely some of the people that increase the publications that reference Zetasizer measurements, right? There's currently about 123,000 peer-reviewed publications that reference Zetasizer measurements in the publications. And I'm sure many of you know that the size range that is usually included within these dynamic light scattering measurements is from about 0.6 nanometers to 10 microns. The sweet spot for any dynamic light scattering instrument is about 1 nanometer to 3,000, but the Zetasizer can measure from 0.6 nanometers up to 10 microns, and I'll show examples of that during this talk. It really determines whether a system is nano or not. It determines size properties, size distribution, the polydispersity of your samples, and zeta potential. Really, zeta potential drives the interactions between particles and the environment. So all of these characteristic tools are there and give you information about your system when you run a dynamic light scattering measurement or a zeta potential measurement. And like I said, there are definitely products where aggregates, knowing whether there are aggregates is absolutely critical to the product. Things like vaccines and drug delivery. Aggregates can be a deadly event in a drug delivery system. So that's where the Zetasizer and dynamic light scattering really shine. So my outline today is I'm going to talk about, again, dynamic light scattering size measurements. We'll talk a little bit about experimental configurations of instruments. You have a Zetasizer Nano. There is a new version called an Advanced Series. And the Advanced Series actually consists of 6 different instruments. We'll talk a little bit about that, and I'll give you some application examples. Then we'll move on to zeta potential, a little bit about the measurements, and again, application examples. When we talk about dynamic light scattering, there's 3 different acronyms that people refer to. They either talk about it as DLS, dynamic light scattering, and it's dynamic because we're looking at how particles move. We're measuring the diffusion rate of particles in a suspension, and from that diffusion rate, we're calculating a size. But historically, there were 2 other names. The physicists originally first called it quasi-elastic light scattering, so sometimes you hear the term Kells. And then there was a time period where the correlator was the most important feature in the instrument. So the name photon correlation spectroscopy really indicates how much concern people had about the correlator, whose correlator was best. And so another acronym is PCS. So again, whether people are talking about DLS, Kells, or PCS, at this point in time, we're really all talking about the same thing. And what we're talking about is measuring size based on the diffusion rate of macromolecules or particles as they move in a solution. And we're obtaining a hydrodynamic size. That's not the size of the particle where the refractive index changes between the particle and the solution. It's the size of the particle along with some ions or things that it absorbs with it. So it is typically a little bit bigger in size than what you would get when you do a microscopy kind of measurement. So just some little movie clips looking at particles and how they move in solution. Again, Brownian motion is the motion of the particles as they're bombarded by the solvent molecules. It's a thermal energy. Small particles move very fast. And this image is actually taken from a nanosite instrument where we look at the scattered light of particles in solution and obtain a particle size, again, by the diffusion rate of these particles. But this is really the basis of how a dynamic light scattering measurement is made. Small particles move more quickly. This is a little movie clip off the internet of milk fat droplets. These are larger particles. They're not moving as quickly, but small particles move more quickly, large particles move more slowly. And again, That's the basis of what we're measuring. So in a dynamic light scattering measurement, we shine a laser on a sample. And because there's not just one particle, there's a lot of particles in that scattering volume where we're shining that laser, we get constructive and destructive interference from that light. And so we get a very noisy light scattering intensity pattern over time. Now we're going to correlate how this light scattering pattern is changing, how that intensity pattern is changing with time. And that's really what this shows. The correlation function is usually represented as g of tau, and it's equal to the intensity at some time t times the intensity at some times t plus tau later, divided by I of t. And all of this is averaged and squared. And that gives us a correlation function that is represented by an exponential decay. Within this function, what we solve this equation for is d, the diffusion rate of the particles. And then we take that diffusion rate and we plug it into the Stokes-Einstein equation. So Stokes-Einstein equation shows that the hydrodynamic radius is equal to kT, the Boltzmann constant, times temperature. We need to know the temperature. 6 divided by 6 pi eta, the viscosity of the solution, which is also affected by temperature. That's why it's really important to know the temperature of your sample. We have a very accurate Peltier in the instrument in order to set the temperature and maintain that temperature. So again, the equation is kT over 6 pi eta, the viscosity, times d, the diffusion rate. So we measure this diffusion rate and we calculate the hydrodynamic radius. The entire experiment sort of goes like this. We have small particles that move quickly. So if we study light scattering intensity versus time, we get a very noisy intensity pattern. If we have larger particles, they do not move as quickly, so there's a more regular pattern in the intensity versus time. But we correlate these signals, and think of the correlator as a photographic camera. If I'm taking photographic snapshots of where those particles are from the start of the experiment to the end, there's some time period where those photographs look almost identical. And then the particles move enough that the photographs don't look the same anymore. And so we lose correlation. So where we start to lose correlation tells us how small or large the particles are. Notice how there's 100% correlation for a longer time period when we're studying large particles versus small particles. So we lose correlation faster with small particles. We apply an algorithm. We apply a summation of exponential fits in order to get a particle size and size distribution. There's actually two ways that we obtain a particle size and get information about the size distribution. There's something called a cumulant fit, and that's where we just apply a single exponential, and from that we get a mean and a polydispersity index. And then there's also a distribution fit that is obtained from the data, which is a summation of exponential fits in order to fit these correlation functions out to a later time period. And that gives us, again, this full size and size distribution fit that you get in your data. So there are two algorithms that are applied. One is called a cumulant fit, and one is called a distribution fit. Just so you know, dynamic light scattering instruments are based on first principles. They're not calibrated. We run latex standards, or we run standards to verify that the instruments are running correctly, but we can't change the results. If they're not running correctly, there's probably something wrong with the instrument, or maybe something happened to that standard. So it is important to occasionally, run a standard, make sure that your instrument is working correctly. There is an ISO standard method. There's actually two of them. This is the older one, but basically you take a latex standard, you dilute it in filtered 10 millimolar sodium chloride in order to suppress that electric double layer, and you measure the size. The dynamic light scattering result is quoted on the spec sheet as a hydrodynamic diameter. This is not actually the certified value on the bottle. That bottle value was obtained by microscopy, but the hydrodynamic diameter is in the specification sheet, and that's the result that you're looking for to compare your result to what you should be getting for that latex standard. When it comes to data interpretation, you should always measure 3 to 5 measurements. Don't just make one measurement, make multiple measurements. The level of the quality of data obtained indicates the level of assurance obtained from the distribution algorithm. The better the quality of your data, the more repeatable the results will be. And what I mean by repeatable is that the count rate, so how much light scattering you're getting every time you make that measurement, that count rate should be consistent. The Z average should not be changing. The PDI should not be changing dramatically between these measurements. What do I mean by dramatically? I mean those values should stay within 3 to 5% of each other. So the count rate, the Z average, and the PDI should not be changing during the course of 3 measurements or 5 measurements, whatever it is that you're making. You should be able to overlay the correlation functions between 3 measurements or 5 measurements. The data that's being fitted by the algorithm, you should be able to overlay that data. The size distributions displayed should be repeatable both by the peak position and the percent areas under the curves. So really good results have very repeatable data, and all of these factors are the things that I look for in deciding whether I have good results or not. The factors within the correlation function that I look for, again, we sort of talked about when the correlation function begins to decay. How much time it takes before the decay occurs tells me how large or small the particles are. This is the basis of my measurement. I watch the correlation function as the measurement is being run. The gradient, the decay rate, that gradient, how steep it is, tells me how monodispersed or polydispersed the sample is. The lower this gradient, the more polydispersed the sample will be. And the baseline tells me whether there's large aggregates, whether there's particles sedimenting, whether I might have something like a number fluctuation going on. If the correlation function doesn't come down to baseline, there's a lot of issues with your data. And again, a number fluctuation is a big problem because during the course of this measurement, let's say we have 500 or 1,000 particles in that scattering volume, we need to maintain the same number of particles during the course of the measurement. If you have large particles sedimenting, that means particles are falling out through that scattering volume, and you're not maintaining the same number of particles. So again, that results in very poor results. That sample is not appropriate for dynamic light scattering. You either have to filter the big aggregates out of that sample or centrifuge the big particles out so that that sample becomes appropriate and can provide good measurements. The fourth feature that I look for in the correlation function is the intercept. The y-intercept, how high that is, tells me how much signal to noise I have in my data. So again, the four key features for the correlogram is the intercept, where the correlation, how much time it takes for the correlation function to start to decay, the slope of that decay, the slope of the decay, and the baseline, whether it's flat, whether it's noisy, whether it doesn't come down to zero baseline or not. All of those are features that I'm looking for while the measurement is running. Let's look at some ideal results. Here's a 200 nanometer latex. This is the correlation function in this little box here. You see an absolutely beautiful correlation function. There's a y-intercept of, I'm going to say 0.9. It's nice and flat. The decay doesn't take too long. It comes down to baseline, and there's a nice clean baseline, no aggregates shown. And again, this is a 200 nanometer standard. So my Z average result is 199.5. I don't think I can get too much closer than that. The polydispersity index is 0.001. So in your report, in your Zeta sizer, it's always printed in red. This is the cumulant fit of the data. So it's always printed in red. It's simply a Z average. It's a mean for everything that's in the solution and a polydispersity index. The polydispersity index is the mean squared deviation divided by the Z average squared. So it's normalized by the Z average. And it gives you basically the Z average is the mean, the polydispersity index is telling you something about the width of the distribution. And again, this is all based on the cumulant fit, fitting a single exponential decay. Then we look at the distribution fit, which is a summation of exponential decays, fitting a summation of exponential decays. And you see that the peak mean comes in at 206, still a good result. And you see an actual distribution. Quite often I get questions about why the Z average size is smaller than the peak mean. You should know that when it comes to samples that are this monodisperse, anything from 0.08 and below, then the Z average result is considered the best result to report. So when a sample is so monodisperse, it actually fits a single exponential decay better than it does the summation of exponential decays. Now, let's talk about really an inappropriate sample. Here is a correlation function, like one I was trying to describe a little earlier. Notice how this y-intercept is barely, it's a bit above 0.3. And it starts off noisy, it decays, it doesn't come down to baseline, and you have very large particles in it. So what does this data look like? Well, this data, one of the biggest flags is that the Z average, the mean, is shown at 653 nanometers. So the Z average is actually larger than the peak mean, which tells you that since the Z average is larger than the peak mean, it's telling you that there are really big things in this sample that we can't fit. And it's really inappropriate for a dynamic light scattering measurement. Again, I could take this sample and maybe I can centrifuge out, maybe I can centrifuge out the large particles and clean this up and get nice data. But as it is right here, with really large particles that don't come down to baseline, noise at the beginning, not really very good signal to noise, and then this Z average being higher than the distribution fit, higher than the peak from the distribution fit, that tells me that these are results I really can't use. This sample, as it is really inappropriate for a dynamic light scattering measurement. So, general quality indicators, having a good y-intercept is really important. And something as high as 0.9 is really considered quite extremely good. It's not ever exactly, the y-intercept is almost never at 1, and it should certainly never be above 1. If it's above 1, then you have that issue of number fluctuations that I was talking about before. Good cumulant fit basically means that your polydispersity is not too high. If you have a bimodal distribution, there are times when the software will flag it and say, well, there's a poor cumulant fit. But if your sample is truly bimodal, then you will still have a good distribution fit, and that data is fine. It's when your correlation function isn't good, like the one we just saw. I hate to use the word good and bad, but if your correlation function has the kinds of problems we saw before, then you can have a poor cumulant fit and a poor distribution fit. And that's when that sample is not ideal for dynamic light scattering. So it's important to have a reasonable count rate. You should have a good cumulant fit. If you have a bimodal distribution, you might not have a good cumulant fit, but you still have a good distribution fit, and then that data is still usable. So those are the things I want to point out here. I have this example. This is really of some antibodies that we kind of used and abused, but I think it's really some telling information. It's a very straightforward example of the kinds of information that you get from dynamic light scattering, but when you're not used to dynamic light scattering, you might ignore. Let's put it that way. So here's an example where, we took really good care of these antibodies for 35 days. We stored them at 4 degrees C. We thawed them out and we made a measurement, and we got this distribution in blue with a Z average of 11.4 nanometers and a PDI of 0.075, so below 0.08. My Z average result is the best result I can report in this case. And again, I have a nice monomodal distribution. Now, I also take one of these antibody samples and I store them at 25 C for 31 days. And then the last 4 of the days I did keep it at 4 degrees centigrade. So I get this distribution that's shown in red. It doesn't actually look very different than the result that I had obtained in blue. I mean, I see this little aggregate out here up around 6 microns, but it's so small, we can overlook that, right? Well, not really. You see right away that, yes, the Z average hasn't changed. The peak distribution looks nearly the same, but notice how the PDI screams at you. It points out the PDI has gone from 0.075 to 0.172. So there is some polydispersity growing in this sample because of the way it's been treated. So you cannot hide from dynamic light scattering. A few aggregates, 1 in a million, or a few in a million, a few in a billion, do show up, and they are shown in things like the PDI or a tiny little aggregate out here that you would like to maybe ignore. It's there, and it's showing up. Now, we really abuse these antibodies. We freeze thaw them through 5 cycles, and now you really see that it's gone bimodal. There's the original size, but there's also a very large aggregate that grows in. The Z average now comes in at 152 with a PDI of 0.65. This is still good data, by the way. You can see that the 152 Z average will be right here, in between the 2 peaks. So this data is good and very usable. The one other thing I want to point out, because I was just talking about polydispersity, is that always keep in mind when it comes to dynamic light scattering, it's based on an intensity weighted distribution. The rawest form of the data is intensity weighted, which means it's based on diameter to the 6th power. If I mix 2 particles, 5 and 50 nanometer particles, in equal amounts in a solution, by number, if I made measurements under a microscope, I would get distributions that had equal-sized peaks of 1-to-1 ratio for the 5 and the 50 nanometer particles. By volume, which is also a mass average, a volume average is 4/3 pi r cubed, so there's a 1/3 power contribution here. Now my peak looks like 1 to 1,000. But by intensity, it is 1 to 1 million. And that's really a big shift between this and this. Now we can, I'm sure you know, you can calculate from an intensity distribution to a volume distribution. And this transformation is not bad. We do need to know the refractive index of the particles, but in order to ensure that this transformation is good. But as a rule, we always say if there's a little bit of noise in this transformation, then we're multiplying our errors when we go to a number distribution. So as a rule, we typically recommend that you do not use a number distribution. Having said that, I've seen data that's very good. I've transformed it myself from intensity to volume, volume to number, and the number distribution was exactly what we got off of microscopy results. So if your data is good, you can make these transformations and your number distribution will be fine. But as a rule, be very careful if you're going to report a number distribution from dynamic light scattering. It's my last, warning. It's my last little caveat. Just always be careful when it comes to dynamic light scattering and number distributions. Just dot your I's and cross your T's before you use them. I want to talk a little bit about instrument configurations and introduce the new Zetasizer Advanced series when I do this. So the beautiful thing about the Zetasizer Nano, which was we first introduced it in 2002, is that we introduced backscatter sizing technology, or we called it NIBS, non-invasive backscatter technology. And what we did, what you have in your Zetasizer Nano is a laser that comes down the side of the instrument. We focus it around the instrument, it focuses into your sample cell, and we detect the light at the backscatter angle. Now, we also, for people who had traditional 90-degree systems in the past and wanted to reproduce their older data, we also sold it as a 90-degree system, but most people, almost everyone, bought it as a backscatter instrument. And it was a huge jump in dynamic light scattering technology back in 2002. To this day, it's pretty hard to meet our specifications. And part of that reason is that not only are we doing this backscatter technology, but we also have this optical lens where we focus into the cell, and we can focus into different positions in the cell. So just to review a little bit, a classical instrument would have been 90 degrees. We bring the laser in. Sorry, I keep touching things. We bring a laser in, we scatter at 90 degrees. We have a cubed scattering volume. When you have backscatter technology, you bring a laser in and you scatter, let's say, at 173 degrees. So you have this diamond-shaped scattering volume that's actually 10 times the scattering volume. So the beautiful thing is that if you have small particles, low molecular weights, low refractive index materials, in this large of a scattering volume, you always get good signal to noise. You always get really nice data. So for dilute samples, as shown in this little figure, you can focus into the center of the cell, you have a very large scattering volume, and you get amazing data. However, on the other side of this, again, because we're bringing the laser in and detecting off the same surface of the cell, that means that we could put this lens in here in the instrument in front of the sample cell, and we could move our focus position. So it turns out, okay, let's say our sample's not dilute, it's very concentrated, it's opaque, that's okay. We can focus now and minimize the scattering volume. We can focus close to the cell wall and try to reduce the other problem that occurs in dynamic light scattering, which is called multiple scattering events. So by being able to focus into different positions in the cell, we can measure very high concentration samples and not have multiple scattering. Multiple scattering is when my sample is so concentrated, I bring the laser in and the light bounces from particle to particle. So my results actually look smaller than they actually are. The particle size results that I get look smaller than what my particle size actually is. So this is the basis of what made the Zeta Sizer Nano, it is the market leader, what has made people want this instrument and use this instrument more than any other dynamic light scattering instrument in the world. So NIBS really provided a unique measurement range. One of the things that from the very start, this is actually blue ink. It is neat. It is 15 weight percent. This is Mont Blanc blue ink. You could never make a measurement of this ink prior to the Zeta Sizer Nano. So color is not a problem in the Nano. Concentration is not a problem. So you can measure it dilute, you can measure it concentrated, but this Mont Blanc ink, which is blue, should absorb some of the red light and should have, signal to noise issues, and certainly should be very nearly impossible to run at this concentration anyway because it's so opaque. Having said that, both of these concentrations are very measurable in the Zetasizer Nano, and it was the first time that Mont Blanc ink could be measured in situ. So let's talk about the Zetasizer Advanced series. It was introduced in 2018, but really didn't get fully introduced until 2020. So it's actually, we stopped building the Zetasizer Nano in 2020, and its full start date is 2020. It is a series actually of 6 instruments. So we're selling a lab system which has 90-degree light scattering, but we've introduced a new type of cell for that 90-degree light scattering. So we've actually created a system that allows you to make size measurements over a broader range, even though you're running in 90 degrees. We're still offering a Pro, which is just backscatter, exactly like the Zetasizer Nano ZS or S. And then we've also added what's called an Ultra, which includes the backscatter, the 90-degree, and still the forward scatter, which is used for zeta potential, but can be used for sizing. So I should go back and say, of course, the lab would have the 90-degree and the forward scattering angle. The Pro will have the backscatter and the forward angle, and the Ultra will have the backscatter 90 and forward angle. And with those 3 scattering angles, we've introduced a new kind of measurement called a multi-angle dynamic light scattering measurement, MADLs. And I'll be showing you some data, showing you some things to explain that it really provides much higher resolution data if you combine the results from those 3 angles, which is what the measurement does. It doesn't combine the data. It's not that it's combining the peaks that you obtain from it's not combining the peaks, the size peaks from the 3 measurements. It's actually combining and weighting the correlation functions from the 3 angles and providing much higher resolution data, as well as particle concentration data as well. And you'll see that in coming slides. So the new features for these instruments is that we're correlating the data differently. Correlation function is being done differently. It's called adaptive correlation, and I'll explain how that's done. There's actually machine learning incorporated into the advice system to give you better information about how to improve the sample and the measurement. There are these multi-angle dynamic light scattering measurements, and that will resolve size differences of a 1 to 2. Historically, dynamic light scattering is very sensitive, but it's not very resolving. You need a 1 to 3 difference in sizes in order to resolve a baseline, to have a baseline resolved distribution. The new instruments can do particle concentration based on that MADLs measurement. There's an extended size range using a low volume disposable sizing cuvette, and that helps the lab instrument give you a greater dynamic range for sizing. There's a narrowband filter incorporated into the optics. If you do have any kind of fluorescence or absorbance, you can just use the software to put in the narrowband filter and remove it. There are horizontal and vertical polarizers available that are in the instrument. You just, again, through software, move them in and out. There's constant current Zeta mode, which helps with life science type applications, high salts, so that you remove polarization effects from the measurements. And the software is completely new. It is more based, it looks more like an iPhone kind of software. So just, I'm not going to spend much time on this, but basically all you need to do in the software is type in a sample name, tell it what kind of measurement, and hit run. And this is what the software looks like. It's a little bit small, but basically you type in a sample name, pick the cell, which determines what measurements you can make with that cell. And then you just pull that measurement, whatever kind of measurement you want, into what's called a method builder. And you can stack those measurements in this method builder. It won't just do one thing, it can do multiple things. And then you hit the green play button, and that's pretty much how the new software runs. It's very user-friendly, and it was actually, the software was designed so that no one had to explain to you how to run it. In fact, I was put in front of the instrument and I was just told, yep, do what you think is best. And so the software is very simple and easy to use. So I've been talking about this new volume capillary cell, and these are little glass capillary cells. They come in packages of either 20 or 25. They're very inexpensive. There's a sample holder, and basically I just use these capillaries to dip them into my sample solutions. I put them in this sample holder, and because of their size, they really restrict convection currents. And because of that, we've actually been able to make size measurements that were really very good at 10 microns and even a little bit above 10, 12 microns. We've gotten very good data in these unique sizing cuvettes. So I've also introduced the concept that there's this new machine learning for the new instrumentation. Basically, what happens is that we've identified certain things about the correlation function. So we know what a good correlation function looks like, what aggregates look like, unstable types of measurements, noisy measurements. And there's a neural network that actually classifies a whole range of issues in the correlation function as your data is measured. And it actually classifies your data into these groups. And then what it does is that it goes through a decision tree and it incorporates really good advice about what you should do with your sample, whether it's good or bad. It also identifies the good data. It's called steady state. The noisier, poor data is identified as transient. It actually saves all the data. In the past, in the Zeta Nano, if you ran 14 10-second runs, half of the data was thrown away. But in this case, what happens is that all of the data is saved, and you can actually go back and see all the data. But you can also just look at what's called steady state data, which is your good data, versus your poor data, which is transient, or you can look at the unfiltered data, all the data. And I've also already said that the instrument is correlating your data differently than the Zeta Nano did. They're now very short subruns. They're 1.6 seconds. Actually, making a size measurement is twice as fast as in the Zeta Nano. We do these 5 1.6 second subruns. And then again, based on the machine learning, outliers are identified and they're set aside. And again, you are grouping the steady state data and the transient data and all the unfiltered data, and all of it can be reviewed. None of it is lost. As in the Zeta Nano, half the data was always thrown away. So now you can see all your data. Actually getting the data is twice as fast. And it's amazing how noisy data is removed, and you're actually going to see that. This is a protein measurement. And if you've ever made protein measurements, you know that they can be quite noisy. There's always some aggregates in there causing trouble. And like I said, and the data is typically quite noisy. But here you have, so this protein was run on the Zetasizer Nano. The same cuvette was just placed in the advanced series. And if you just look at the steady state data, there's 5 measurements there, just like there were 5 measurements, maybe more here. I'm pretty sure in the advanced series, this is a backscatter measurement, and there were 5 measurements, and you see how reproducible the results are, as well as the transient data is completely removed. When it comes to MADLs, the multi-angle dynamic light scattering, the key to keep in mind is that there's an angular dependence to light scattering data. Larger particles scatter more in the forward angle. Smaller particles scatter more isotropically or equally at all angles. And so if you take the rawest form of the data, the correlograms, and weight them appropriately based on the angle that you're making your measurement at, you can actually get higher resolution data. And like I said, you can split a distribution down to 1 to 2 with this technique. So this is actually a milk sample that was done. Again, this is the Zetasizer Nano. The same cuvette was put in an advanced series instrument, and you can see that this distribution, the primary distribution around 500 nanometers, is actually made up of casein micelles and the fat emulsion, and you can resolve those 2 peaks in this data. So that's an example of MADLs, but I think I have additional examples as well. This is just a statement, but it's really from that MADLs measurement, again, based on the me theory and the angular data that you get. You can also draw out particle concentration from particles that are anywhere from under 10 nanometers up to 500 nanometers. You can get particle concentrations, and again, you're going to see an example of that coming up. So just to go into applications, once again, there's really a broad range of applications that can be covered by dynamic light scattering. One of the nicer examples, the way that an example of how we spec the lower end for the Zetasizer Nano, for instance, is that we published data showing sucrose. The molecule is, whether you're running sucrose or dextrose or maltose, depending on what sugar molecule you're looking at, we can actually size it somewhere between 0.6 to 0.7 nanometers, depending on the actual molecule and what its size is. So this data was published and is one of the examples of how we set the bottom specification for the Zetasizer at 0.6 nanometers. We are also able to measure cholesterol, which is, I think, 0.62 nanometers. So as far as particle concentrations go, this is a 30 nanometer gold sample. It's produced by the National Physical Laboratory, which is the British laboratory that is identical to our NIST. So in the US, we have NIST. In the UK, they have NPL. Just to show you that making a measurement on these 30 nanometer gold standards that they produce, that the MADLs result is really very similar, very close to what you can get from disk centrifuge, which is a very highly resolved kind of measurement, right? You're fractionating the sample, you're getting an exact number-based, almost number-based sizing result. And it is one of the methods that they use to confirm the size of their gold nanoparticles. So that's what we were compared to. And the Maddles result is basically identical. But the other nice thing is that the concentration measurements were also used. So the particle concentration measurements on the ultra were also used, and you see a very linear result over a wide range of concentrations. So you see how you see how broad of a range we can make concentration measurements of, a monodispersed sample like this. That same sample was measured, as a function of hour on the first day, and then it was measured for 5 days. So the 30 nanometer gold, you can see how reproducible the size results were. The size and the size distribution results were very reproducible by dynamic light scattering on the Zeta sizer ultra. And this actually shows the peak size with the standard deviation across the 5 days that the gold was measured. You can also see the concentration for fresh aliquots that were taken every day. And these are the concentration results, again, off the Zeta sizer ultra using that Maddles measurement. UV-Vis data is shown in red, so how we compared to UV-Vis data for particle concentration. Another example that I wanted to show is, this is an example, again, using Zeta sizer ultra and looking at the Kraft point, or the critical micelle temperature for surfactant of pluronic F68 at a concentration of 10 megs per mil, which is over the CMC concentration. So pluronic F68 is a EO-PO copolymer surfactant, and its Kraft point is above 52C. So what we did was we looked at the light scattering count rate as a function of temperature. So we put the cell into the instrument, and we just looked at how much light scattering, the count rate that we got as a function of temperature, and you see the inflection point just above 52 centigrade. So that's how this study was done. But just to show you, so we also did a Maddles study, a multi-angle dynamic light scattering study. And as I said, this study is done at, you do a backscatter measurement, a 90-degree, and a forward angle. So you do get the size results for the 3 measurements. And then, and at the same time, the software takes those 3 correlograms and also combines them to give you a Maddles result. So just to show you that the data is reproducible from the 3 measurements, but it is not as resolved as the kind of result that you get from the Maddles. And what's really nice about this data, so from 45 degrees centigrade to 52, you see pure unimer, right? You see pure single monomer particle size results up until 52C. And then at 53C, from the Maddles result, you see unimer with some micellar sizing. And as the temperature increases, you get more and more of the micelle after the transition temperature, after the CMT transition temperature. So I think this is, very nice results, very resolved results showing, the original unimer versus, the unimer with, the equilibrium unimer with micelle and the micelle concentration growing as the temperature increases. It's just very nice, very resolved kinds of results. When it comes to dynamic light scattering, the benefits of it far outweigh any issues as far as I'm concerned. It's a non-invasive, non-destructive technique. You need very small quantities. It's very sensitive. You need less than 0.1 megs per mil for typical proteins in order to be able to measure them. You have low volume cells. In the nano, the smallest volume is 12 microliters, but in the advanced series with that new capillary, you can go down to 2 microliters. Scattering intensity is proportional to the square of the molecular weight or diameter of the 6th power, however you want to think about it, but a few aggregates are very easily identified by dynamic light scattering. And you can, there's software in there where you can estimate molecular weights. I did have a slide in there, but I removed it because I already have a lot of slides, and I think actually it's past 5 o'clock for me, and I haven't gotten to zeta potential, but maybe we should stop it here.
I think so too, Aina. Thank you so much. Maybe we'll have to do another seminar on zeta potential, especially. So, but I think in interest of time, it'd be good to let the students, whoever's still on the call, ask some questions. If there are questions, and I will also look in the chat to see if anybody is posting anything there. So please, if anybody has a question.
I do have one, although I may have missed it because I came in late. I was on a different meeting. So I was under the impression that depending on the size, you would get a different volume integral for that, which means that large particles, even if you had only a few of them, they would show up as looking like they're a lot bigger or more of them. Now, you gave this nice comparison of numbers, volume, and intensity. And so it sounds like maybe the approach to that would be to actually do that measurement.
Yeah, so what you measure is the intensity, and then the software calculates the volume and the number for you as well. So you can compare those values. We often say the very best result is the peaks by intensity, and that the volume distribution, which is the mass distribution, really indicates more, is more realistic to what's actually in your sample. So the percentages by volume, but the peaks by intensity.
And okay, go for it.
Sorry.
No, I was curious about that conversion. Is that something that's in the software that we can find in terms of how those calculations are done? Or we always just get a number that gets spit out by the instrument, but does that data live somewhere that we actually can access?
I mean, the actual data is there, but I mean, there are application notes that explain the equations.
Okay.
I can send those to you.
I see Kim has her hand up.
Could you hear me?
Yes.
Yeah.
Yes. I have a question about our particle. So we are interested in the anisotropic particle, but is there the necessary aspect ratio for that to check the two exponential decays?
So if it depends on how long, like if it's a wire, usually the result, if it gets really long, the result usually ends up being the length of the wire. I mean, otherwise you're getting like an equivalent spherical diameter. The one nice thing that is in the Pro and the Ultra, the new instruments, is that there is a vertical and horizontal polarizer. So you could see if there was some rotation. You can see that there is some anisotropy using the polarizers. But you can't really calculate how much of the what the ratio is. You can't really calculate even from that. But it does give you some information. I can send you an application note about that as well.
Yeah, so when I calculated our polymer ratio is over than 7.5 versus 1, but it seems only one decays of the correlation refractive correlations, and the size and the intensity, we only could see one peaks in there. So I just make a question about that.
Yeah, so did you get the 7.5?
2, 1, yeah. The length and then the
It's
diameter.
mostly the length, yeah.
Yeah, okay, I'm gonna try again. Yes.
Any other questions? And maybe another question from my end. I know in the data fits you have a high resolution model. I know with the molds you'll get that actual high resolution data, but in the data processing high res mode, does this just do something to improve just it's just manipulation of the data, or is it actual using data differently?
No, it's actually, so the fits of the data is actually done by non-negative least squares. And so there's general purpose, which is pretty much what everyone uses. And that's still non-negative least squares, but we've allowed the alpha parameter to allow for smoothing, to make it look like smooth curves. Multiple narrow modes is full-blown non-negative least squares. So we haven't played with that alpha parameter. It's just full-blown non-negative least squares. And if your data is good, like there isn't a lot of noise in it, you should be able to get nice distributions from that non-negative least, from that multiple narrow modes. Especially, because proteins are discrete, right? They might be a monomer, dimer, octamer. Like I see multiple narrow modes providing really nice data there. That's an example of where it works really well.
Got it. Okay.
Yeah, I can send some application notes so that you have some background about the intensity volume distributions, how they're calculated, and then how, and also some things about the polarizer.
Okay. Any other questions? Okay, if not, thanks again, Anna. It was really nice
Yes.
to
Thank
see you, and thank you for that talk. It was useful.